MSM3. Here we go, Unit 6, Triangle Side Length Relationship. So you will notice that we are diving headfirst into geometry. You'll be working with different squares that have side lengths of 5, 6, 7, 12, and 13 units. You will be using the squares to create triangles, which sounds really silly unless you actually see what I'm talking about. So the question is, if you have a 5 by 5, a 6 by 6, and a 7 by 7, can you make a triangle with those? So the empty space between the squares needs to be some sort of triangle. So if I move these squares around, is it possible to make a triangle with that empty space in between them? And the answer is yes. You just have to get a little bit creative. And there we go. We've got a nice triangle in there. So a 5, 6, 7 triangle is possible. Side of 5, side of 6, side of 7. But what it's saying is we're using the squares that are 5 by 5 squares, 6 by 6 squares, and 7 by 7 squares to create that. So all the possible groupings. So we just found that a 5, 6, 7 triangle is possible. Okay. So what are the possible ways that we can group those 5 numbers? So 5, 6, 7 is one group. 5, 6, 12 is a group. 5, 6, 13 is a group. Well, I don't have any other ways to do 5 and 6. So 5, 7 with the 12, 5, 7 with the 13. Notice I'm not going to do 5, 7 with the 6 because it's already back here. And then let's see, how about 5, 12 with the 13? Well, I've done all the ones that I can with a 5, so I'm not going to use 5 anymore. If I start with the small numbers again, 6, 7, 12 is a group. 6, 7, 13 is a group. I've exhausted all my 6, 7 pairs. So 6, 12, 13. That's all the ones that have 6 that weren't already back here in my 5s list. And now 7, 12, 13. Those are all of the possible groups that I can use my squares with. So you can see I have a square for each size. And if I try to actually make those triangles, which ones are going to work? So 5, 6, 12, for example, 5, 6, 12. If I put the 12 square and the 6 square and the 5 square, I cannot get them close enough together to close up and make a triangle because 5 and 6 are not long enough to compensate for this side that's a 12. So we would say that 5, 6, 12 didn't work. It didn't make a triangle. I think we could all agree that if 12 didn't work, 5, 6, 13 is also not going to work. Not big enough. So how about we try 5, 7, 12? So 5, 7, 12. So here's the 12. Let's put the 7 and the 5. And I don't get a triangle. What I get is a straight line because 7 plus 5 actually equals 12. So that is also not a triangle. 7 plus 5, not big enough because they equal 12. And if 5, 7, 12 didn't work, 5, 7, 13, obviously not going to work because the 5 and the 7 wasn't long enough for the 12. What we probably notice at this point is that there seems to be a pattern. How can we figure out whether or not something's going to be long enough? Well, we said that 5 and 7 added up to 12 and they weren't long enough. But if you go back here to the one that did work, 5 and 6 add up to more than 7, which made it possible for them to form a triangle. So one thing that we can notice is the 2 shorter sides must have a sum greater than the longest side. And we don't say like first and second because we don't always get sides that are in order, smallest to largest. So we always want to identify which 2 of the sides are the shortest. So for example, on here, 5 and 6 were the short sides. They added up to more than 7. So if we make a guess, the 2 short sides here are 5 and 12. Do they add up to more than 13? Yes. If I have a 13 and I have a 12 and I have a 5, can I make a triangle out of those? Definitely. I definitely have enough 5 and 12 to make a triangle with the 13. So that's going to work. So if we just take a look at all the rest of them, this one worked. 6 plus 7 is 13. 7, 8, 9, 10, 11, 12, 13, which is more than 12. So that one's going to work because the 2 short sides add up to more than the longest. 6 and 7 with the 13. So let's check that one out. Here's the 13. What happens when we add 6 and 7? It adds up to exactly 13, which is why we cannot make a triangle. The 2 short sides always have to add up to more than the longest side. So that one is not going to work. 6 and 12, that definitely adds up to more than 13, and 7 and 12 adds up to more than 13. In both cases, right, the two short sides add up to more than the longest side. So we can always check those. We can always look for the inequality. 5 plus 6 is greater than 7. 5 plus 12 is greater than 13. 6 plus 7 is greater than 12. 6 plus 12 is greater than 13. And 7 plus 12 is greater than 13. So it said to circle all the groups above that will form a triangle and cross out all the groupings that will not work. So if we circle the ones that we put our check marks next to, those are the ones that will work. We also can just sort of do like a quick flashback, types of triangles. Acute triangles, a triangle has 3 acute angles, meaning all of the angles are less than 90 degrees. Right triangle has 1 right angle, 1 exactly 90 degree angle. And obtuse, one angle has to be obtuse or greater than 90 degrees. So what we're going to do is we're going to look at the ones that we just found that worked. So these are the 5 groups of numbers that worked on the front, and we're going to see what type of triangle they make. So for example, let's start with 5, 6, 7. So if we have the 7 with the 6 with the 5, the question is, what type of triangle is it? Do we have an acute angle or all acute angles, any right angles? And this one's really hard to tell. It actually looks like it could be acute or it could be right. So let's use one maybe that's a little bit more clear. Let's use, for example, the last one, 7, 12, 13. So here's 7, 12, and 13. If we put them all together here and make a triangle, that one is definitely acute. No question about it. All 3 angles less than 90 degrees. So the 7, 12, 13. Let's look at that one first, the last one on the list. If we do the A side, which is considered the smallest in this case, we've put smallest to largest. If we do 7 squared, we get 49. The B squared, if we do B squared, we get 144. And the C squared, C always has to be the longest side. 13 squared, that's 169. So I just want to clarify, C always has to be the longest. A and B are sort of interchangeable, the 2 short sides, like we said before. So if we add A squared and B squared, we're adding 49 and 144. Are they greater than, equal to, or smaller than the remaining sides squared? So 49 and 144, if we add that up, we get 193. So is 193 greater than, less than, or equal to 169? It is greater. All right. And we said this was acute. So what we're going to do is we're going to collect data based on what we build. So the next one, I'm going to build the 6, 12, 13. So 6, 12, 13. Let's see on that one. If I build a triangle for 6, 12, 13, it's kind of close, but that one is also acute, just under 90 degree angle there. So 6, 12, 13, also acute. If we do the 6 squared, which is the smallest side, we get 36, 12 squared, 144, and 13 squared, 169. If we add the 2 sides squared, the 2 shorter sides, we are adding 36 and 144. That adds up to 180. Is that greater than, less than, or equal to 169? Also greater than, and we also found that that was acute. So what we're saying, our hypothesis, is that if it's going to be an acute triangle, the A squared plus B squared has to be greater than C squared. The 2 short sides squared have to be greater than the longest side squared. And if we look at building those, so for example, if we look at the 12, 13, 6 one again, what we're saying is that the number of squares here in the 6 squared, the 36 squares here, plus the 12 by 12, which has 144 squares in it, their area is bigger than the area of the longest side squared. All right, 6, 7, 12. So let's see what happens with that one without the pieces. So 6 squared is going to be 36, 7 squared is going to be 49, and 12 squared is going to be 144. The 2 short sides, A squared is 36 plus B squared is 49. When I add those together, I only get 85. Is that greater than, less than, or equal to the longest side squared, 144? It is less than. So if you were going to take an educated guess, when it was greater than, we got acute triangles. What do we think it's going to be for 6, 7, 12? Let's build it. So here's the 12, here's the 6, and here's the 7. And you can take a look, that angle pointing down, definitely obtuse. So this is an obtuse triangle, 6 by 7 by 12. And we've got a new rule, obtuse. So an obtuse triangle, which is the third one down here, what do you notice about the relationship between the sum of the areas of the smaller squares and the largest square in an obtuse triangle? We just found that if a squared plus b squared is less than c squared, we get obtuse. All right, so let's color code these. The two acute ones, we had a squared plus b squared was greater than c squared, and that was for acute. The next one, the one we just did, when a squared plus b squared was less than c squared, we had an obtuse triangle. So again, let's make a hypothesis. If it's going to be a right triangle, would we expect it to be greater than? No, that's acute. Less than? No, that's obtuse. So a right triangle, let's see, we might have one left. 5, 12, 13. So if we build a 5, 12, 13 triangle, that's where we get our right triangle. And it's tough to make it perfect when I'm moving around little slips of paper, but right here we have a right angle. If we take a look, I made on a separate piece of paper, right? If I try to put the 12 and the 13 with the 5 on the long side, it's not going to work because 5 is not the longest number. If I had a 5 by 13, let's see, no, 12's not going to work, right? Because the right angle doesn't fit there. But my last one that I made, let's see, if we put the two short sides, the 5 and the 12, making the right angle, and then we sneak the 13 in on the remaining side, you'll notice that you get a perfect right triangle. The 5, 12, 13, right? This side is 5, this side is 12. Here's your right angle. 13 is the longest side. So 5 squared is 25. The next side, the short side, 12. 12 squared is 144. And then the longest side, 13, is 169. What happens if we add a squared plus b squared? 25 plus 144, 169 is equal to 169. And we got a right triangle. So anytime you have a squared plus b squared equals c squared, that's your right triangle. Now, the first one, we were having a really hard time telling whether it was going to be acute, right, or obtuse. Well, we're at a point now where we've made relatively decent hypotheses about how to tell if it's acute, right, or obtuse. So instead of building it, let's look at the numbers. 5 squared is 25. 6 squared is 36. 7 squared is 49. Does a squared, 25, plus b squared, 36, compare to 49? When I add them together, I get 61, which is greater than the longest side squared, 49. And we said if a squared plus b squared was greater than c squared, it was acute. So it was tough to tell whether it was acute or right, and that is an acute triangle. It joins that group. We've now discovered that if you know the side lengths of a triangle, you can tell what type of triangle it is. Determine what type of triangle, acute, obtuse, or right, would be formed if it was 5 inches, 5 inches, 5 inches. So first thing I'm going to tell you is make sure that you identify the two shortest sides. So 5 inches and 5 inches are the two shortest sides, and then the remaining 5 is going to act as our longest side. So we would do 5 squared plus 5 squared, and then we would put an equal sign with a little question mark over the top because we don't know if it's going to come out equal or not. I'm going to guess not, because 5 squared is 25. Plus 5 squared is another 25 equals 25. Well, that doesn't make any sense. 50 is definitely greater than 25. And when a squared plus b squared was greater than c squared, that told us it was acute. The next one, 3, 4, 6. First, I want to make sure that I identify the two shortest sides. So make sure you've got them underlined, highlighted, something so that you use the two short sides and not just the first two listed. So we're going to check 3 squared plus 4 squared. Does it equal 6 squared? And we don't know. We put the little question mark over the top. 3 squared is 9, plus 4 squared is 16, equals 6 squared, which is 36. So 9 plus 16, if I add those together, I get 25, which is less than 36. So if I look back up here, when a squared plus b squared is less than c squared, it is obtuse. Maybe I knew that ahead of time, and that's why I colored it green. Now on the remaining one, 6, 10, 8, I want to make sure that I highlight or underline the two short sides. Again, not always the first two in the list. So make sure that's your first step, identifying the two short sides. Then you're going to have a squared plus b squared equals, with little question mark, c squared. 6 squared is a short side, plus 8 squared, which is a short side. Does it equal 10 squared? So we're testing whether or not 36 plus 64 equals 100. Notice I did all of those exponents in the same step. 36 and 64 adds up to 100, which equals 100, and that would tell us it is a right triangle. So very easy to test now that we know the three rules. Acute triangle, a squared plus b squared has to be greater than c squared. Right triangle, they have to be equal. And an obtuse triangle, a squared plus b squared has to be less than c squared.